So let's summarize week 8 now, the key topics we've covered. We start off thinking about traveling the galaxy, taking our twin paradox analysis and applying it to the possibility of a trip to the center of our galaxy, approximately 30,000 light years away, which would seem, even at the speed of light, it would take 30,000 years to get there. So it would seem totally impractical to do that. And yet, using our twin paradox analysis, which of course is based on time dilation, length contraction, the relativity of simultaneity, we showed that for the person on the rocket, if they could get up to a high enough speed, which would be very close to the speed of light, then they could even reach the center of the galaxy in 2 years and then come back roughly in another 2 years. So that was good news in a sense. It would be very interesting to take a trip like that. The more sobering news, however, is that when we thought about the energy actually involved to do that, not to mention the practical consequences of how do you take enough food along and so on and so forth, but we talked about the famous equation, Einstein's famous equation, equals mc squared, the more general form of it being equals gamma mc squared, and we saw that when we reduce that for the low velocity limit, 0.1 c or below approximately, it turned into equals mc squared, the famous part of the equation, plus a kinetic energy part. And so we identified the mc squared part with the energy associated with mass, that somehow mass and energy are equivalent to each other, and one can be turned into another. And so we gave them the usual examples of nuclear fission and nuclear fusion, talked a little bit about that in qualitative terms, how that relates to equals mc squared there. Then we turned our attention to the general theory of relativity, just a few of the foundational concepts there. Talked about Einstein's, what he said was his happiest thought, his most fortunate thought of his life, and that came in 1907 when he realized that essentially being in an accelerated frame of reference, such as if you're in an elevator that's accelerating upward, that is equivalent to being in a gravitational field, being in that elevator just on the surface of the Earth and feeling the force of gravity pulling you down. And using that, what became known as the equivalence principle. So again, we have the equivalence of energy and mass from here, but this is a different equivalence principle, and that is the equivalence of an accelerated frame of reference, being in an accelerated frame of reference, in other words, you're accelerating, and a gravitational field. And what that allowed Einstein to do was to do thought experiments, especially in an accelerated frame of reference, like an elevator accelerating upwards, and derive certain consequences of that, and then say, well, because of the equivalence principle, it must be the same way for a gravitational field. And these were his initial forays into what became the general theory of relativity. And we pointed out two consequences of this equivalence principle, the qualitative derivations of them. One is gravitational time dilation. In other words, that in a gravitational field, because we showed this for an accelerated frame of reference, that a clock up here versus a clock down here, okay, this clock, the bottom clock, closer, really feeling more gravity, as it were, would run slower than this clock. Right? Or clocks higher up in a gravitational field will run faster than clocks lower down. And so that was one result that came out of the equivalence principle. Second result, again using sort of an elevator analysis, was that light would bend in a gravitational field. So those two results came out of this idea of the equivalence principle. And then we went on to talk about just several final comments. One of those was the idea of crucial experiments. The popular idea of science is you get an experimental result. If it's against a theory of the time, then you must throw the theory out. But we pointed out that theory is built into experiment as well, the theory-ladenness of experiment. So in many cases, you're not quite sure what's wrong. And so we cited the example of experiments by Walter Kaufmann of Germany right about the time of the miracle year that essentially disproved Einstein's version of the special theory of relativity and Lorentz's related version as well. And the data seem to be good. The results seem to be good. Max Planck pointed out a few things where it's not quite as clear-cut as maybe Kaufman made it out to be, but still they were concerned that, what are you going to do, Einstein, with this? And Einstein's response essentially was, I'm going with my theory, because my theory is based on very fundamental general principles, and these experiments and some of the alternative theories they seem to support were more ad hoc in nature, not as general, and so on and so forth. And it turned out a few years later, about 10 years later or so, that as they continued to do more experiments, that there were some flaws found in Kaufman's earlier work on this. So that was one crucial experiment where it was rejected. The results were rejected and turned out to be right. Another example were the 1919 eclipse expedition results that seemed to show, that did show, the bending of starlight in the around the sun, in the gravitational field of the sun. The question was whether the bending actually matched up with Einstein's prediction or not. And again, we cited it to indicate the human element of some of these things, because you have to, in data analysis, you have the data there and you go, do we throw out that data point because we think it's bad, something went wrong with that measurement, or maybe we keep it in because we think it's a good measurement, it just doesn't fit what we think it should be, and so on and so forth. So in the end, they did announce in 1919, the British expedition led by Arthur Eddington, that it was in favor of Einstein's theory, was confirmation of Einstein's theory, and that really was the beginning of Einstein's rise to fame, not only in the scientific world, which he had been fairly well known before that, but in the general public, in the realm of the general public as well. So crucial experiments. Said a few words about the nature of genius. One of the things we mentioned was it's the combination of passion plus time spent on task and going deep into a subject, plus talent. So it's not just talent, it's not necessarily just time, it's not necessarily just passion, but it's a combination of those, and to a certain extent being in the right place at the right time. Einstein came together with his background, his upbringing, the things he was passionate about and thinking about, and the insights he was able to generate from all that in a way that we would call genius. And it matched up with some of the key problems of the time, and he was able to make progress there. Later on in his life, he wasn't quite as successful, although he did, certainly for the next 20 years or so after 1905, he seemed almost every couple of years he'd come up with a new result. Even things we didn't get a chance to talk about in this course, but even modern-day things like lasers go back to some of the theoretical work Einstein did in the early part of the 20th century. So Einstein's fingerprints, as it were, are throughout modern science, not only in relativity, but also in quantum mechanics and in many other ways as well. So that was a few words on the nature of genius. And then relativity versus relativism. We noted they're very different things, although people often confuse them. And in fact, somewhat ironic misunderstanding, because relativity really is a theory of invariance, the unchanging quantities, while relativism as a philosophical theory says everything's relative and everything changes in a sense that way, or you can't choose between things, as it were. And then finally, just ask the question, is all this really real, this time dilation stuff and length contraction and the twin paradox and everything else? And we said it actually is. It is part of the marvelous structure of reality. One of the original quotes we quoted from Einstein, that it's the way the world works. We have good experimental evidence for it from, we cited the example of muons, the GPS navigation system, particle acceleration, and so on and so forth. None of that makes sense without the underlying foundation that Einstein provided with his special theory of relativity and then later on his general theory of relativity.